is Christopher Schafhauser, who's going to be telling us about KK-rigidity of simple nuclear systems.
Thank you. The first, thanks to the organizers for the invitation and all the work putting this conference together. I've been here for 2 weeks now. It's really been a great time. It's a very nice chat. Yeah, so I want to talk about this KK rigidity, which is related to some things Jamie talked about earlier, but not equivariance now. They grew out of, but it's very much in the classification problem. So state classification term here. If A, B are unital, separable, simple, nuclear, Z stable, C star algebras in the UCT class. Then they're determined in a simple sense by KK traces, which we tend to consider to be computable. So K theory, K0, K1, T the tracial state space, T is a compact set. The pairing between traces and K0. And so if you have a trace on the algebra and a projection and some matrix over the algebra, you can evaluate some trace the projection. And the extra data where the unit sits inside the K0 group. Right. So that's saying several times over the week. And the assumptions, I mean, there's a lot of them. It's in practice, they are actually verifiable, especially for, say, if you look at group-wide algebras and first 4 conditions, you know, separable, simple, nuclear, we know how to decide these things hold. UCT for dynamical examples tends to come for free by the results of Higgs and Kasparov and two on Baum-Kahn theory, and then extended to the twisted case by Barlock and Lee. And even more concretely, if you're actually able to compute the K theory groups of whatever C star algebra you wrote down, you can probably just look at the proof and see a proof of the UCT inside of it. Compute the K theory by breaking it into smaller pieces, and the UCT has very nice permanence properties. And Z stability, there's a lot of active work on. I actually verified that in dynamics. As I saw in, for instance, Wilhelm's talk, and depending on what the problem is, you might just be able to tensor out a copy of Z and make it Z stable. If the example you want is. So, yeah. It's conditions are actually, you can check, typically covers very large classes of examples. The problem I want to talk about that's been around for quite some time, even some special cases before the theorem was proven. What do you do without UCT? Of course, there's a very famous question of is you even need the UCT, is up to all nuclear C star algebra satisfy UCT. If you just delete the UCT from the theorem, it's either that the UCT was automatic or the theorem becomes false. It's the value. You can exhaust all possible values of the invariant with UCT algebras. So it's more if you actually had hypothetical non-UCT nuclear C star algebras, can you enlarge this? They throw KK data into the classification variance and still say something. This is Jamie mentioned earlier in the purely infinite case. So when there are no traces, he is empty. This is what the Kirchberg and Phillips did in their proof of the Kirchberg-Phillips theorem. That Here. A to B are say equal. Here's where algebras. Which. So the with unitable, separable, simple, nuclear, purely infinite, which is the same as and under the arc is the same as the stability plus infiniteness. But no UCT. There exists invertible. Element KK with that preserves the unit ID. And then if you combine it with the UCT by a separate algebraic computation, any isomorphism of K0 and K1 it came from an invertible element of KK. To get back to the usual the isomorph between K0 and K1, preserving the unit in K0. Is an invertible KK element and then an isomorphism. Some of the analytic parts of separating the analytic parts of designing the algebras are isomorphic, and the algebraic parts of designing the KK equivalents are completely separate. There. This, by the way, this is the kind of thing I mean by a KK-rigidity result of a KK class remembers the isomorphism class. The basic problem is there any form of this in the finite case? And well, I'll say first, so this is trace is not, there is at least one trace. We'll say first the proofs behave very differently from infinite versus finite C-star algebras. You collect the statements into one sort of artificially by saying, well, the trace simplex might have been the empty set. But yeah, the proofs the whole way through have very different structure for a large part. So UCT plays a major role, not just at the end, computer KK class, but at intermediate steps. And actually a very subtle role. It just like shows up through the in the starlight either stable uniqueness theorem. What actually happens is it enters in sort of some kind of abstract compactness argument where you try to turn a pointwise bound into a much more uniform bound. It's not just turning homotopians something more rigid. It's far deeper than that and far harder to isolate from the rest of the argument. But one could hope for some better way of doing this. A Gauss conjecture, it's going to be somewhat vague and they've been around quite some time in various forms. And I don't know if there is any precise formulation of it. But to say something like if A and B are same classifiable conditions, let's say unitable, separable, simple, nuclear, stable. Let's think in the finite case. Importantly, not with the UCT. Possibly not with UCT, I suppose. And there's an invertible element in KK. Which these KK elements, think of it as a homotopy, invertible KK element, think of it as a homotopy equivalence from A to B, or maybe a homotopy after transferring with the compacts. It's more general than that, but of the same form, trying to get some kind of homotopy equivalence between matrices. Preserving units. and an invertible affine, so a continuous affine. So an affine homeomorphism between the trace spaces. So with that, I have the invertible KK element is inducing a isomorphism on K0 and K1. I have the isomorphism on the trace part. Assumed I preserve the unit. The missing part of the invariant should be some interaction between K theory and traces. So that kappa and gamma should somehow have some kind of compatibility, and I'm being intentionally vague there because I don't know what that compatibility condition would look like in general. But then you want it to be isomorphic. That I have one candidate for a compatibility condition is exactly this one. Your kappa does induce a map on K0, and I can exactly ask that the K0 map and the trace map are adjoints under like that pairing in the same way we demand on the other invariants. I'm not convinced that if in a hypothetical world where there are non-UCT C-star algebras, I'm not convinced that's actually a strong enough condition of something else, but I'd be happy with just about any form of this that's true.
Would it predict to be true if you knew the actual verb homotopy equivalent with a homotopy satisfied? Which is a traces of the both.
Yes, this is true. This is one of the results, talk about even if there is a homotopy equivalence from A to B, which induces an isomorphism on traces, it is true. Yeah, that's one of the new results here, that under some conditions that there's some hope. Abstractly, yeah. So yeah, that's some progress on this as well. I'd say something about. I should say maybe before I stay in this result, though, there's a natural question up here if every example I can write down and anything coming from any sort of reasonable dynamic does satisfy UCT. So there is some question of why would you want this? It's in some sense it'd be sort of nice to be able to separate out the KK part from the K theory part, like happened with here Phillips theorem. But maybe more importantly, in K, if you start trying to push past just classifying the algebras or simple nuclear C-star algebras and some purely infinite setting, there's Kirchberg's classification of strongly purely infinite nuclear C-star algebras outside the simple case, involving some kind of ideal related KK theory in place of KK, or what Jamie talked about this morning, outer actions of discrete amenable groups on Kirchberg algebra involving some kind of equivariant KK. These, I think, are things that are reasonable to aim for in the finite case. Have C-star algebras with some ideals or with some group actions or with extra structure and some other kind. If you need the UCT at these sort of intermediate steps and actually have to know how to compute these KK groups, this tends to be far out of reach even when you have some kind of equivariant UCT. These KKG groups that Jamie talked about are ideally KK groups that came up earlier. Even in relatively small examples, there's not really satisfying UCTs like the HOM X one for normal KK. That you somehow have to, the goal is really put all the hard computational, all the hard algebraic topology parts you have to compute in one place. And then in small examples, there is very good chance one can still say something. This is what happened with all the results we talked about this morning about these X2 elements or even the similarity class of an element in the representation ring. It goes through KK gamma, you just don't need a full computation of it. Or the results already talked about the group actions, outer actions of groups on Kirchberg algebras, having some connection to stable homotopy theory invariance, also very much go through Gabe-Szabo equivariant Kirchberg Phillips theorem, and the ways these things have used despite having a complicated invariant. And I think any hope of doing this in a stably finite case is going to involve something like this and not having to dig into how these things are actually computed. What I want to say is don't have a full solution to this. I want to say something, there's some progress towards it though. Some special cases where you can say something. This is last fall. If A and B are very nice classifiable C-star algebras, let's say finite, strongly self-absorbing. So self-absorbing, C-star algebra is self-absorbing, if A tensor A is A, absorbing itself under tensor product. And then the strong condition is, the isomorphism between A and A tensor A is approximately mutually equivalent, just embedding into the first factor. That these turn out to form a very rigid class of C-star algebras. So by Thomson, introduced by Thomson Minor, by the way. They all, okay, by definition, unitable and separable. They all, what the proof from the conditions are all simple nuclear Z stable. And have extra, even much stronger structural properties I don't want to get into, but they are in this class minus UCT. Here, the result is true. Then A is isomorphic to B, different only if there is an invertible kappa. They're KK equivalents in a unit preserving way. It's just that these algebras also have unique trace, finite ones. So this isomorphism in trace space is just there because they're, the one point spaces are isomorphic. And whatever mysterious compatibility condition that there might be turns out to be automatic for some mysterious reason in the strong self-absorbing setting. But there's been a philosophy for a while that was largely pushed by Wilhelm that these strongly self-absorbing algebras should be a test case for general classification problems. They're incredibly rigid. For instance, if you have two such things, A and B, if A embeds into B at all, then there's only one embedding up to approximate trade focal lengths and also up to homotopy. So but the fact they're always in the classifiable setting, they have a bunch of extra properties. You get these sort of uniqueness of embeddings when they exist for free. That this extra structure makes classification problems easier. And they somehow are still general enough that they can shed light on what happens in the general case. But the conjecture is at least true here, which is a good sign that there is some hope.
And you're making order structure and traces, of course, is trivial anyway in that case.
There's no order structure involved.
Traces don't want them.
Yeah. In fact, even in general, the order structure you can quickly recover from the pairing, in the simple nuclear C stable case. For strongly self-absorbing algebras, order structure, trade structure, or pairing. So I don't need any of it. It really is the KK equivalence gives the isomorphism.
Also, KK could potentially pick up also that.
I have tried. I wasn't able to do anything with that. There's a corollary. These algebras, there is a reduction to the purely infinite case, because if you assume if A is self-absorbing, so is A tensor O infinity. If these are isomorphic, then tensor with O infinity change KK, so you have the same. There'll be KK equivalent from that isomorphism, and you can somehow cancel the O infinities and go back to the isomorphic P. So it can actually cause a diagonality, but it does answer this problem you posed a while back, that if O infinity tensor Q is the second largest FSA algebra, then all the finite ones are quasi-diagonal. But I couldn't get any farther try to get quasi-diagonality from it. Yeah. But it's kind of using this reduction from the finite classification to the infinite classification in some sense. Looks these drawings of absorbing case. And when I saw this, I got excited and thought, really, if you can do an drawing self-absorbing case with enough patience, it'll work. I couldn't quite get there. I think it's largely just really having no good idea of what this, how traits and KK interact. To somehow hiding in special case. But like you can part ways still, if A and B are again classifiable, but without the use of T. Several simple nuclear Z stable. And instead of having an invertible KK element and some invertible map gamma on traces, I'm going to ask that, well, I have those things, but they're both induced by the same star homomorphism. A unital. So that phi and here phi. So I have, again, the kappa is square bracket phi, the gamma is the trace map induced by phi. Just assume they came from somewhere, not just given to abstractly. Yeah, there does even star homomorphism with these properties. Then it is at least true ways, isomorph would be. And part of what's happening here, whatever compatibility condition one has between the data, if it's going to be natural, it has to, the star homomorphisms have to satisfy it. So, I can't write down the compatibility condition. I can say safely that any reasonable one will be satisfied. But you do end up with a nice one. You do end up there. Right.
Yeah, I think marketing would be better in this case than some way you negative change.
Yes, that's fact. I mean, the thing you really want to know is that there's an isomorphism inducing the KK and trace map, and I can't quite get there, but you can get close. You can make it approximately, equivalent to 5. So we'll induce the same map on traces because traces are continuous and unitary invariant. It almost induces the same map on KK. There's there's some quotient of KK called KL, produced by McKell, that they will agree there, which is somewhat very approximately agree on KK in some sense. But yeah, it is in one way or another built out of 5.
They're not making it from trust me, you said it for
Yeah, I don't know how to get asymptotic equivalence for sure. I expect it's possible. So. Yeah, proof does not give asymptotic equivalence, but I'd be very surprised if it's not true. Right. And maybe make this. You get rid of KK here, make this a bit more grounded, so say that, you know, several simple nuclears, he's stable. With enough projections or very few traces, they projection separate traces. So imagine an algebra with unique trace or one with real rank 0 or enough projections in the sense there. Then you can drop the trace data because the isoforms then keep. You'll know what's the ability to cover the traces from how they paired with the projections, which you can see by the K0 group. And the easiest way to get a KK equivalence would be through a homotopy equivalence. So if A and B are homotopy equivalent in this study, then they're in fact isomorphic. Wait, so the homotopy equivalence by definition comes with the homomorphism from A to B. That's my P. Being a homotopy equivalence, the homotopy inverse gives you an inverse in KK, and then project separated traces forces to be bijective on the traces. So you're in this previous setting. The part where the that it was KK-rigidity, it's sort of, there's a very different context, but in the spirit of many of these homotopy or rigidity results in topology, where for nice manifolds like spheres, if they're homotopy equivalent and they're isomorphic. But so it's a sort of topological rigidity reacts. So you start studying very different kinds of objects, but same application at the end. Right. First drawback of these things is since there's no nuclear C-star algebras known with loads of T, there's no actual sample for it. It wasn't just a classification there, but the fact is a weak form of classification theorem, we're assuming there's map to start with. But the real hope is, yeah, be very optimistic. You start throwing ideal structures, group actions, tensor category actions, whatever extra bells and whistles you want, and you have a suitable kind of map that agrees that invertible on whatever variant of KK is needed, and then this will still hold. And it really, I don't have that it results in that direction, just, I think it's a proof of concept that it sets up my hope is it sets up a template for how one might prove subject invariant results and get stably finite versions of the things like Jamie and Robert were talking about earlier about classification of finite group actions and flows and moving the UCT all to the end into the complicated KK group gives you, turns the problem into being a KK group, which is in kind of small examples, topological methods and algebraic methods can sometimes do it. All right.
And these projections here, they're only there to make sure the quantities are.
Just to get rid of the trace part. Yeah, so if you had a homotopy equivalence, which happened to be an isomorphism on traces, you have the same conclusion. It's because the homotopy equivalence is a KK invertible. Yeah. Yeah, it's just entirely cut the traces out and give it a cleaner nation. It does not simplify the proof in any way either. Yeah, it's part of that thing off this off, project separating traces is often a crucial assumption, so you could get some extra structure on the C-star algebra from this. It makes no difference in the proof here, whether it's that condition or not. Okay. So that's answers. So I want to just give some very brief overview of what's going into this and highlight oh, you get, how one drops, how one is avoiding UCT. So idea why I think there is at least some hope that eventually these things will be done. Maybe overlaid settings or that. The proof of here we go, it's here, this one. So there is a map, we have this map A to B invertible and KK and traces, and you have to somehow build it. Well, deform it to have an inverse. And if you, for those who have dug into any amount of this classification, there's a standard, it's these all go back through intertwining arguments. Almost any form of abstract isomorphism where you can't just write down generators and send them here. The intertwining arguments are usually what these things go through. When it comes to it's enough. To construct a unital map in the other direction. Which is an inverse up to approximate integer equivalence. This is Elliott's two-sided intertwining arguments. From here, you can conjugate P and psi around by unitaries, take limits and get additive inverses of each other. That's where the P hats will come from. Second reduction, it's not to do half of this. And basically, it's the conditions on P and psi or conditions on A and B are symmetric. So I'm gonna say something slightly false here, but I'm gonna go with it anyway. The psi phi, if I have on KK, psi phi is the identity and phi is invertible, so psi must have been invertible. I catch it, okay, some KL in there, it works. Don't worry about it. But what is actually true, trace phi, trace psi is the identity, and trace phi is invertible, so trace psi is invertible. So if you should have shown that every phi has left inverse, then your left inverse psi also has left inverse. Depending on B. But then put a P on both sides and, you know, this usual uniqueness of identity or uniqueness of inverse proof from say in groups, the P prime and phi had to be equivalent. So phi psi is a two-sided inverse for phi.
The fact that this starting of the axis comes from the theorem that you just erased.
No, I was only in the strong self-absorbing case was yeah. So my claim is it's enough to show any such phi has a left inverse.
Mhm.
And if you can do that, then I apply back to the left inverse and. So phi prime if I assume psi exists for all phi,
Yes.
psi is such a phi, I get a. Phi prime is the new psi,
Mhm.
so, yeah. And one last reduction and. Instead of aiming for a genuine star homomorphism, it's enough to do an approximate version of this. The easiest, the cleanest way to do this is, Look at the lower Walsh power of A, the sequences, module sequences way to 0. Makes no real difference if you do this with an ultra power, just the usual sequential limits over the naturals. F might C. Oh, F might C0 is just fine for. It's enough. So given the phi, there's a psi from B not into A, but into A omega. That's inverse of psi. And I'll bet sentence a second, but. What is that? That's, you don't have a genuine star homomorphism B to A, you have, say, a unital completely positive map B into A. A sequence of, say, unital completely positive maps B into A, which in the limit preserve multiplication, and in the limit act as a left inverse for phi. And I want to turn those approximate maps into a genuine one, and to do that, I have to ask for something a bit more. That's that this side is unique. So here's where the intertwining standard intertwining arguments will get to us. If you want to build the map A into to construct the map A to B, or B to A as his left inverse, it's enough to build a map B into A omega, acting on as left inverse. As side B is the diagonal inclusion. Psi phi of A is the constant sequence A. All right. I go till 10 minutes. Perfect. Thanks. So the final piece of this, there's this proof of the classification theorem from here that was posted a few years ago by myself with Jamie Stewart, Aaron Quetius, and Jose Carrion. What came out of this is under, say, classifiability assumptions, or a bit more generally, a classification of embeddings from one, say, B into A omega in this case. And this we did without the UCT at the expense of a rather complicated invariant. And well, but inside of this J sub A, inside this A omega, there's this ideal, this trace kernel ideal. This is all elements which are 0 on all traces on A omega. This is of course a very big C star algebra, but it's becomes reasonably well behaved because it inherits a lot of properties from A. And the quotient, in a unique trace setting, the quotient is even a 2-1 factor. So the quotient is also relatively well behaved. With several traces, it still has enough properties of a 2-1 factor to be useful. And so this is Zakaria and Gabe. The. Aaron Quacious and Stuart Whites. That this, I'll say, embeddings. So an informal version of this. B into A omega, classified by. So if you want two embeddings are saying, are mutually equivalent, there's, first they have to agree on trace. And then there's a secondary invariant in some KK group. What happened was when we did this in our proof of classification theorem, we used T entered at this point to compute that group in terms of the K theory of B and J sub A, and then unwind that, turn it back into something about A omega, which we can actually use. There was a lot hiding, and there's a lot hiding behind B UCT assumption to push that complicated invariant back into something that's actually useful for A. What's happening here essentially is you can, if you get by without actually computing that and use as a secondary invariance, it's enough, it's just enough to run the same kind of intertwining arguments and get an isomorphism at the end. I'm not very and over, so it's not bad. Thank you.
Question.
I'm curious, philosophically, you view this as a way of approaching the UCT, or it is something that is most interesting with the UCT both.
It was partly a hope that, I'd become a bit obsessed with trying to prove things I know with UCT, trying to prove them without UCT.
Yeah.
Like that, I don't have any actual line of attack. My hope is that at some point you learn enough about KK or get stuck somewhere and it starts to give some insight of something about KK of nuclear C-star algebras. So it was partly, can you get any insight on the UCT by just trying to prove the affect things without it? But yeah, I don't have any concrete line of how to approach UCT.
But when we say that, that Phillips theorem, I mean, that was just natural to prove without UCT. I mean,
Right.
natural to use KK theory, but here it seems like that's a problem.
Yeah. Yeah, I mean, I think it's,